Okay, so right, so we did problem one. I think everyone did problem one last time, and now I just kind of want to. I was gonna like work through problem two together and then put you guys in groups, but now that we're on Zoom, I don't know. I can just maybe I'll let you guys start the problems for a couple minutes and just like, and then we can sort of talk about them or something without going fully into breakout rooms and stuff. So let us do that. Let me share my iPad screen now. Oh, it says a plugin is required to share. Okay, hopefully that won't take too long. Yeah, let's see how this works. Okay, so hopefully you can see that. I can see it on the screen, kind of. So I'll just write the problem. So this is number 2. And it says, so basically it gives a function x cubed minus xy squared minus x, and a constraint x squared plus y squared equals 5, right? I can't find the iPad screen now. Hold on, let me stop the share for a second. I think sometimes I'm sorry, give me a second here. Ridiculous. Okay. Okay, so this is the problem, right? You guys can see that. Okay, so remember the way the Lagrange multipliers works is we're going to set, we're going to have f of x, f sub x, the partial x is lambda times g sub x. And we're going to have the partial y equals lambda times g sub y. And then we're going to have the constraint equation also. And then that will give us the 3 equations and 3 variables. So yeah, take a minute and write out these 3 equations. Like maybe I'll let you guys get ahead of me. And if you're with other people, you can like do it together, compare notes. People in the classroom could write it on the front board if they want. It's up to you guys. If you feel comfortable doing that. It's kind of fun to see people in the classroom. I like this. I should just teach remotely all the time and be this voice, and just have you guys in the classroom. So take a minute, try to write out the partial x for f and the partial y, and then the partial x for g and partial y for g. If I change the view, does it change? Like if I okay, so I also put a hint in the problem that was like conclude as much as you can from the partial y equation, because I do think if you do so that's the partial x, right? 3x squared minus 2xy minus 1. So what you guys are getting, and lambda times 2x there, and then the partial y. Oh wait, I can't differentiate. What am I doing? It's just minus y squared, right? Yeah. And then the partial y is the minus 2xy. And that's lambda times 2y. Try to make my lambdas and 2's not look the same. And then the constraints x squared plus y squared equals 5. So these are the 3 equations and 3 unknowns we have, right? And I said conclude as much as you can from the partial y, because this one's more simple, right? This is a simpler equation. And maybe we can actually do some stuff with this. So first off, we could say, let's just get rid of the 2 minus xy equals lambda y. And then if we sort of follow this down, I mean, I've talked about this before about instead of canceling the y, let's put everything on the same side of the equation. And then factor out the y. So you get that, and that means that either lambda equals negative x, right? Because the first thing is 0, or y equals 0. So you can sort of conclude, you know, it's one of those, we're in one of those 2 situations, yeah? Again, please add questions or jump in and, you know, either put questions in the chat or jump in and ask if something seems wonky to you, or if I do something wrong. Okay, so let's do the lambda equals negative x case first. So if that's true, we could put that, right, we have lambda in the first equation. So we could replace this lambda right here with negative x. Right, so we get 3x squared minus y squared minus 1 is negative x times 2x. So that's negative 2x squared. Man, my 2's and lambdas look kind of similar. Okay. And then if we rearrange, what do we get? I think we get y squared is 5x squared minus 1. Which, you know, you might think, okay, then what does that tell us? I mean, we can get y in terms of x, but we also have the constraint, right? So with these 2 equations, we could plug y squared in there. And then that means, you know, x squared plus y squared equals 5 would then imply that x squared plus 5x squared minus 1 equals 5. Okay, so this isn't too bad at this point. So x is plus or minus 1. I think I contrived this to work out nicely. And then if x squared is 1, well, we can then go back into here, right? We can plug that in here and get y squared. So y squared is 5x squared minus 1, which is now going to be 4. So y is plus or minus 2. Okay, and then, so that gives us 4 points to check, namely 1, 2, negative 1, 2, 1, negative 2, and negative 1, negative 2, right? There's no direct relationship between x and y with the signs. Like, I think there's only squareds. I don't think there's anything in these equations that would let us actually say that like x and y are the same sign necessarily or anything. Yeah. Okay, fair. So it's those 4 points. Now, here's the thing. If you didn't, you also need the y equals 0 case. And I actually I think I contrived this so that the y equals 0 case is where the actually the most important points are. Now, if y is 0, you can look back at all three equations and think about what that means. But I don't think, well, so y equals 0 actually came from this equation. So that makes that equation hold. Y equals 0 here just would tell you something about lambda in terms of x, but again, lambda is sort of like a dummy variable. And so, but then y equals 0 here is clearly the helpful thing, right? So then that means x squared is, if x squared plus y squared equals 5, then this would imply x squared equals 5. And so you get two more points, the positive square root of 5, comma 0, and the negative square root of 5, comma 0. Right, and we have all these 6 points to check. And then that's what's super important, is that you need to find these points, because I actually think I contrived this problem. I said I put this on exams in the past because students like to miss these kind of cases, these kind of extra cases where you're like, if you canceled out the y up here and didn't spin off the separate case y equals 0, that you'd actually would be in trouble. And I think I contrived it so that the maximum endpoints are actually these two, but we can check, right? So if you're trying to find the maximum in values, so check, which was x cubed minus xy squared minus x at these points. So let's see, if we plug in, notice y is only squared, so I think we can put plus or minus 2 here. We can check these 2 points simultaneously because it's going to be the same. So you get 1 minus 1 times 4 is 4 minus 1, which is negative 4. If you plug in this one, you get minus 1 plus 4 plus 1 minus negative 1. So you get positive 4. If you plug in the square root of 5 comma 0, well, root 5 squared is 5 root 5. Plugging in 0 gives you 0 there, minus root 5. So that's 4 root 5. And plugging in negative root 5 is something very similar, I think. So that's negative 4 root 5. And actually, these are the bigger values, right? This right here is the maximum value. 4 root 5 is bigger than 4. And this is the minimum value. Okay. Does that make sense? Any questions about that? It's a little surprising. I did actually plot. Let me share Mathematica with you guys. So I did actually plot this surface and this. Well, that was the visualization we had before, the very first Lagrange problem we did. But here's the surface. Let's see if I can make this a little bigger. Sorry. If I actually plot the surface, x cubed minus xy squared minus x, it's kind of a monkey saddle type thing, right? But then if I actually restrict to that circle, this circle, you can kind of see the top view. There's a circle, that's the circle. But you can actually see, yeah, there's these 4 points that get identified by the Lagrange multipliers process, which are the plus or minus 1, plus or minus 2, plus or minus 1, comma, plus or minus 2 points. You can sort of see those are local minimums, right? It like gets up, it goes up. It is that thing where like it's touching a contour and then going back down. But there's actually these two higher points, higher and lower points, like the highest points here and the lowest points there. And those are actually, yeah, correspond to plus root 5 comma 0 and minus root 5 comma 0. So again, this would be very hard to visualize. So that's why we use this method instead to find all these points. Cool. Any questions about that? All right. Okay, so then let's just maybe, again, I'll have you guys start number 3 sort of on your own or with people around you, or now it's a function of 3 variables. So you've got to do partial x, partial y, and partial z equations, right? So before I switch back to the notability, I'll write it. Let me just write it down in the file. So I think I use capital F because I was in this era of always using capital F and capital G for functions of 3 variables. I think some books kind of do that. But you have this kind of strange function, x squared, y squared, z squared. And the constraint here is x squared plus 4y squared plus 9z squared equals 27. That's actually an ellipsoid shape, like an egg shape. And so, right, so you're trying to find the points on that egg shape where this function x squared, y squared, z squared is maximized. Okay. So again, trying to start this. This one's a little bit, it could be unpleasant, but I do think there's ways to make it, there's ways to organize the logic to make it not completely unpleasant. Switching back to the notability, and I wrote the problem there. So I'm really not writing up in words. I should just say like max min of this with the constraint of that, right? So again, try to get ahead of me here. You're going to write out all of these equations now, right? So now you have 4 equations and the 4 unknowns. So again, take a minute or two. I'll sit here and drink coffee. In particular, once you have one of these equations, it's good to like try to figure out what you can conclude from it. All right, I'll should be able to get this sense of what these partials are for F, right? There's something like this. The partials for G are not bad also. This is HY, right? This was lambda times 18Z. So if you look at the first equation and you cancel what you can cancel twos and you can cancel x's, but remembering that also you could have x equals 0, right? So this is x equals 0, or if you cancel 2x from both sides, you get y squared z squared equals lambda. This is y equals 0, or x squared z squared equals lambda. And this is z equals 0, or x squared y squared equals lambda. Now, here's the thing where the logic could be a little bit unpleasant, is that you would really have like 8 possible cases, because I could have like these 3, or I could have like this and this and this, or something like that, right? Or I could have this and this and this, or this and this and this, or this and this and this, and etc. Right? There's all sorts of, since I'm trying, I have to, all 3 of these equations have to be satisfied. So, so it looks like a lot of cases, except if you think about, sometimes you do want to keep in mind what the actual function you're trying to maximize and minimize is. And if any of x, y, or z are 0, if any of these are 0, then you can see what capital F is, right? In that case, capital F is just 0. So that's a nice thing to sort of keep in mind. I guess let me just write that constraint over here before. Oh, nope, I miswrote it. Hold on. Okay, so yeah, so let me write that out in words. So if any of x, y, or z equals 0, then capital F equals 0, because it's the function is x squared, y squared, z squared. And that's clear, and that's also clearly a minimum value, because there's no way for this to be negative, right? So that's actually the sort of the minimum. Okay, so now it's going to be more a matter of finding the maximum. And that's going to, so now if we assume they're all not 0, then we're really just in the case of these 3 things being true, right? So we have all 3 of these simultaneously, because none of these cases are kind of, we just ruled out all of these cases where any of those are 0. Does that make sense? I don't see anything in the chat, so. Okay, so otherwise, but I guess I'm just saying that's a place where you want to keep your head about you a little bit, because it just seems like there's a lot of cases and it could get unpleasant quickly. Although I guess as soon as you start exploring these cases where x, y, or z is 0, then you would see that, you would realize what was going on, sort of. So otherwise, we have y squared z squared equals lambda, which equals x squared z squared, which equals x squared y squared. Oh, I messed up. Nobody's yelling at me for when I messed up. Why is no one yelling at me for where I messed up? You guys are supposed to yell at me. You see where I messed up? There should be a 4 right here. Is that right? And there should be a 9 right there. Sorry about that. Yeah, I can't. I just forgot that they had those coefficients. Okay, so let me try this again. So otherwise we have lambda equals y squared z squared. I could say I could divide the quarter over x squared z squared, and I could divide the 9 over to make 1/9 x squared y squared. So these are all true, right? And we know x, y, and z are not 0 because we've ruled out those cases. And so this, let's see, this would imply if we canceled the z squareds here, we would get y squared is 1/4 x squared. And if we canceled, I guess I can try to put everything, we're going to want to use the constraint, right? So I guess we could try to put everything in terms of x. So if I also compare these two and cancel the y squareds, then we get z squared is 1/9 x squared. Right? And then now you're going to plug these into the constraint. So you get x squared, really 4y squared is x squared again, and 9z squared is x squared. So you end up getting that, I think. So x squared is 9. So x is plus or minus 3. And then from these equations, we can figure out what y squared and z squared are. And if you think about the function, we really just need to know y squared and z squared. We don't really need to know y and z, but I think this means, let's see, that means y squared is what, 9/4. So y is plus or minus 3/2. And z squared is 1. Okay. So now you have, there are 8 points here, I guess, plus or minus 3, plus or minus 3/2, plus or minus 1. But the point is, once you plug any of these into the function, we already found the minimum was 0, right? If any of x, y, or z is 0. But then this is just 9 times 9/4 times 1. Did I get that right? So it's 81/4. And that's the maximum value. Yeah. All right, how are we doing? Any questions about any of that? Give everyone a minute to catch up and breathe. Go ahead and start writing problem 4. Maybe this one I will talk about the setup, because the setup's kind of more interesting. And maybe also I'll talk about why A and B are the same problem. And then and then we can and then I can let you guys work on it. But so I got a question in the chat. Is the only reason that 81/4 was the max because it's positive? Yeah, we found that minimum was 0. Just because X, Y, or Z could be 0. There are points with with one of those coordinates 0 satisfying the constraint. And then right, because all the other points we found all have the same value of the function, and that has to be the max. 0 is the minimum, and then 81/4 is the maximum. So good. Thank you for the question. Now, if you look at problem 4, it's kind of an interesting question. So I give you this surface. It turns out, I'm just copying it out of the notability. It turns out that this is a sphere. You can actually complete the square on each term and recognize it as a sphere. And then it's not too hard to find. So since it's a sphere, it's a contained surface. Therefore, it has like a minimum X coordinate and a maximum X coordinate. Like it's got a, there's like a minimum Z and a maximum Z. There's a minimum Y and a maximum Y. And there's a minimum X and a maximum X. But how is this a Lagrange multipliers problem? You could almost see it as if you solve for X in terms of Y and Z, of course, there'd be like a plus or minus somewhere, but you can almost see it as like a max and min of a function of two variables, Y and Z, and actually finding the critical points of those functions and finding all that, right? But I want to sort of think about why this is a Lagrange multipliers problem, or how you could actually reframe it as a Lagrange multipliers problem. Let me go back to the iPad. Okay, so here is the question. So this right here, this is a constraint. Right, so that's a constraint equation. So let's call that, g of x comma y comma z. But what's the function that we're maximizing? Are we finding the maximums of? Can anyone tell me what the function is? Put it in the chat if you want. If you have a guess. Max and min x value. Yes, good. Somebody put in the chat. Right, it's just the function x. It's kind of a funny thing to think about, but if you want to maximize x, you just maximize the function x. It's sort of deceptively simple answer, right? And so it's kind of a neat idea that, okay, it's just that any point x comma y comma z, you can you want to find the maximum x value. So it's like you just want to take the x out of the x comma y comma z. So that's a way to do that, is this function. Good. And now it's not too bad, right? And then it's Lagrange multipliers again. Actually, in this case, I might put the lambda on the other side because this is such a simple function. It's going to have a nice, the partial x is 1, the partial y is 0, and the partial z is 0. Like the gradient is very nice, just 1, 0, 0. So actually, I started to write f sub x equals lambda times g sub x. But actually, let's write g sub x is lambda times f sub x. Because g is this function up here. So the partial x is just 2x minus 4. So we get 2x minus 4 is lambda times 1. Yeah, once you set this up, it's not too bad. Because now the partial y is 2y plus 2, but that's lambda times 0. So that's just 0. And here we get 2z is lambda times 0. And so immediately we get y is minus 1 and z is 0 from here, right? Which is kind of nice. And to find x, we would just use the constraint. I guess this equation actually is not very helpful because lambda is just some kind of dummy variable. And it's not going to tell us much. But if we use the constraint, so if we plug those into the constraint, so we get x squared minus 4x plus, what is that? 1 minus 2, maybe? Plus 0 plus 1. And hopefully this will work out nicely. Oh, I think it's just that. Everything cancels. And so that's x times x minus 4 equals 0. So that means x is 0 or x is 4. So the points, I guess, are 0, minus 1, 0, and 4, minus 1, 0. But if we're just finding the maximum and x value, then it's clearly, we're just looking at the x values, right? So this is our max. And this is our min. Yeah, so it turns out that this is a sphere. In fact, yeah, I'll just write this here. So in fact, if we take x squared plus 4x, what was it? I lost the constraint somewhere. Oh, y squared plus 2y plus z squared plus 1 equals 0. These first two terms we could add, we could complete the square by adding a 4. The next two terms we can complete the square by adding a 1. So I have to add 4 plus 1 to the other side. The plus ones cancel, and you get x plus 2 quantity squared plus y plus 1 quantity squared plus z squared equals 4, which is 2 squared. So this is a sphere centered at oh, wait. Did I do something wrong? Oh, there's a minus. There's a minus here. Again, you should yell at me or throw that in the chat as soon as you see it. I guess these are all minuses. So sphere centered at 2, negative 1, 0 of radius 2. And now this answer up here becomes quite plausible, right? That like, if it's centered, if it's radius 2 and its x coordinate of its center is 2, then you can at least go at most 2 to the left and 2 to the right. So from 0 to 4. So, okay. Any questions about that? Really, the hard part there is just identifying that it's just the simple function x. It's kind of, like I said, deceptively simple. Okay, this was actually for a 4B was a problem that we've seen before, I think in section 14.5 about 3D gradients. But it was like find the points on, or find the points, maybe plural, on this same surface whose such that the tangent plane at that point is parallel to the YZ plane. That's what problem 4B says. Okay, now this is a problem about gradients, right? So because tangent planes are parallel, I mean their normal vectors are parallel, right? That's kind of the thing that that's the first step we should always make, right? Tangent planes parallel implies normal vectors are parallel. The normal for the YZ plane is in fact I, right? I vector is I 1, 0, 0. The normal for the tangent plane is given by the gradient, right? Again, if we call this function up here, G. So the normal for the tangent plane, it's really the same thing as normal to the surface, right? Is the gradient of G, which is 2x minus 4, comma 2y plus 2, comma 2z, like that. And to say these two vectors are parallel is to say if the gradient of G is lambda times the grade times I for some lambda, right? But do you start to see how this becomes exactly the same problem? Right? We end up with, basically we're saying we end up with 2x minus 4, like the gradient of G here is 2x minus 4, 2y plus 2, 2z. And the gradient lambda times 1, lambda times 0, lambda times 0. And these are exactly the same equations that we had. And it makes sense too, because the points that max and min x point on the sphere are going to be the tangent plane at those points is going to be like, it's sort of max x. It's the tangent plane is going to be like a maximum, it's going to be like a peak, but with respect to x as a function of y and z. So its tangent plane is going to be quote unquote horizontal. It's going to be like parallel to the yz plane, if that makes sense. So it's the same answer. Okay. I do feel like I took some of the fun away from you by just going through these problems, but hopefully you were getting ahead of me and doing them on your own. Or maybe between Wednesday and Friday, you did the whole problem sheet just for your fun, for yourself. Okay, so maybe just one last thing. If I go back to this, this is not in the textbook, but I kind of like it, is that you can actually do like a 2 constraint Lagrange multiplier. Like I want to maximize or minimize some function with respect to like 2 constraints. And then it does turn out that like you get some sort of generalization of Lagrange multipliers. which is something kind of crazy like this. It's not obvious why that's true. Yeah, I said here, it turns out that the gradients all lie on the same plane as opposed to lying on the same line in the one constraint case. But I will say, like, this becomes an interesting problem to solve. Like this, you could solve this a couple different ways, like highest and lowest points on the intersection of these. Like this is a plane intersecting a bowl, right? And you could try to sort of maybe eliminate a variable and turn it into something, you know, you could try something, but I just want to show you the visualization of this because I think it's kind of cool. I think I have this under in Mathematica. Yeah, down here, I actually drew the plane and the bowl intersecting. And you can see that there's, you know, they intersect in kind of this ellipsoid shape or ellipse shape. And you can actually see that there's a maximum point up here and a minimum point down here. And you could use some of the geometry and symmetry of the situation to sort of realize, oh, probably y. It's kind of the 2 points are on the line where y is negative x maybe, or positive x, like y equals x or y equals negative x, because like there's a symmetry in x and y. And oh no, y equals x, I guess, yeah. And so you could actually sort of make some arguments to find the points that way, but you might try doing this as a Lagrange multipliers problem. It's kind of a neat problem. So, but we're going to be out of time, so we don't have time to do it. But all right, thank you for bearing with me. I appreciate again the people in class, in the classroom, sort of, you know, putting everything up on screen. And like I said about the, you know, the write-ups, you have the weekend, but hopefully you've already done quite a lot of it. And yeah, so let's just call it a day. Hopefully my eye won't be screwed up again. It's getting better a little bit, like hour by hour. So I might be around this afternoon. So yeah, in fact, I said I'll have office hours now, like in Gather, but then this afternoon I have an office hour at 2:30 and I should be in the office. So okay, take care, everyone.
Thank you.
Thank you.
Thank you.
you.
Thank you.